Okay, so today we're going to be designing model predictive controllers, mainly for two examples. We will be working with a drone hovering problem, where our goal is to regulate the height at which this drone is hovering. In particular, we would like to regulate the drone at the same height of a nearby cliff. And we will be designing a model predictive controller also for an autonomous racing example. So let's start with our drone hovering problem. Here we will consider in this example a problem where we have 1 degree of freedom. So our drone can move up and down along the vertical direction. And our goal is to design a controller that hovers in place at a specific height. And this height, again, is the height of a nearby cliff. And we are going to be measuring the position of the drone starting from this nearby cliff. So our goal height is going to be 0. And furthermore, while designing this controller, we want to make sure that we don't hover too high, as there are perhaps wind turbulences, and also we don't want to hover too low, as we don't want to hit the floor. And in this simple example, the state of the system is going to be two-dimensional. It's going to be the position along the vertical axis and the velocity. And I've chosen this simple example because with this two-dimensional state, we will be able to build some intuition and to plot the trajectory of the system on a two-dimensional plane. And in this example, our goal is to design a controller that commands the acceleration that is given to the system. So our input u equals to the acceleration. So here we are assuming that we have a low-level controller that, given our acceleration commands, decides how fast we have to spin the propellers of the drones. And in this simple example, we assume that the system evolves following discrete time linear system, where the position at the next time step k+1 equals the position at the current time step plus the velocity multiplied by a coefficient. And so in this example, we have some inertia because we cannot immediately control the position of the drone. We can affect only the velocity, again, giving a specific acceleration command. And in this example, we would like to regulate the system to a constant height. Again, the position is measured from a nearby cliff. So our objective function is given by the summation of two quadratic terms. And the last key points that we are going to consider, again, are state and input constraints. And so we will assume that we have some safe regions where we want to operate the system. And the key point here is that we have also some saturation constraints. So we cannot command infinite acceleration. So this system is not easily controllable because we have some saturation on our actuators. And so this is the problem that we are going to look at today. So I would like to stop for a second to see if there are any questions about the notation and the problem that we are trying to solve. Okay. And as we discussed last time, computing a control policy that maps state to actions is challenging because we have state and input constraints. So this is not a linear quadratic regulator problem. We have state and input constraints, and it's hard to compute a control policy. So what we are going to do is that we will apply a receding horizon technique, where the key idea is that at time t0, we are going to measure the state of the system x at time 0, and we are going to plan, using the batch approach that we studied in the previous lecture, an open loop plan. So we're going to plan a sequence of optimal actions and an associated trajectory. And so in this particular example, we are looking 2 steps into the future. And now, given this optimal plan, in receding horizon control, we apply the first element of the optimizer vector. So what we see is that our drone will move close to our predicted trajectory. And at the next time step, we can iterate this procedure. So we measure the state of the system at time 1. And again, we're going to plan a new different trajectory that here is depicted in red. And given this new trajectory, again, we're going to apply the first element of our optimizer vector. And so we see that with this strategy, we actually managed to design a policy. So now we have a strategy that, given a state of the system at a particular time, computes a control action by solving an optimal control problem via the batch approach. And so here, the key idea is that at each time t, we're going to plan different trajectories. So here, what we see is that the plan at time 0, and which here is represented by this old planet trajectory, is different from the plan at time 1, simply because we have changed the initial condition of the system. And so any questions about this receding horizon strategy to compute a control policy? Okay. And this idea is fairly intuitive, and indeed it was proposed a long time ago, already in the 60s, and actually I believe there are some similar strategy already in the 50s that use this idea. And since then, it has been interesting topic of research. I just want to underline two current research directions, which are very active, and those might be also idea for a final project. So the first research direction is how to integrate learning, and in particular model-based learning, with this receding horizon idea. So and in particular in this research thread, the key word is safety. So when we use historical data to learn the system dynamics, we have some model mismatch between what we plan and what actually happens in closed loop. And so people are doing research to see which are the sufficient conditions that guarantee that we don't violate our safety constraints. And the other direction of research is how to use machine learning to compute the solution to our batch approach faster. And there are several research labs, including some of ESONC students, some people at Stanford and at Princeton, that are trying to incorporate learning to speed up the solution of batch approaches. And also I want to underline that solving solving the finite time optimal control problem using the batch approach is a current area of research. And if you will go and work, for instance, for Tesla, Google, Apple, all these big companies, they have a department which is designed exclusively to design solvers for computing the solution to the batch approach. So now let's see how this strategy actually works on our drone example. And in particular, I would like to compare the performance of our model predictive controller with a linear quadratic regulator. There are only two differences between the model predictive control strategy and the LQR controller. The first difference is that in MPC, we plan an optimal trajectory over a finite horizon. On the other hand, in LQR, we plan the optimal trajectory over the infinite horizon. And the second difference is that in MPC, we do consider state and input constraints, whereas in LQR, we only consider the system dynamics and the initial condition. So in this figure, we see the closed loop trajectory resulting.
Why do we only consider the infinite horizon case in LQR?
Oh, good question. So it's not that we only consider the infinite horizon case, it's that we can. So in LQR, as we did in the last class, we derived the optimal solution for the infinite horizon optimal control problem. So ideally, we would like to plan our trajectory from now until our task is completed. So it's not why we plan over an infinite horizon in the LQR, it's more that we cannot plan over an infinite horizon for MPC.
Maybe I can just comment briefly.
Yeah.
The infinite horizon LQR problem has a closed form solution. So there's a certain level of mathematical convenience to studying it as well.
Mm-hmm.
You could just call MPC just constrain LQR, is that right?
Yes, exactly. But again, the key question is like constrain finite time LQR. Because again, we plan over a finite horizon, and this will cause problems, as actually we will see in today's class.
May I ask a question?
Oh, sorry.
Oh, yeah, go, Chris.
Oh, thanks. I thought last time we did the finite horizon LQR case, and I also thought that LQR with an infinite horizon, like you have to solve like a for finite horizon LQR, there is a like iterative solution. For infinite horizon, then you have to like one way to get the optimal controller is to iterate this iterative controller like until it converges or something like that.
Yes, so it's a great question. If you as you pointed out, we solved this dynamic programming recursion, and we were going backward in time, and we keep updating this feedback gain k. So our solution, our input u at time t was equal to k at time t times x at time t. And what's going to happen is that if you iterate this recursion for some finite time, actually this gain k will converge. So you will have that if you keep iterating, you will have that u at time t is equal to k times x. We didn't see this in class, but iterating this recursion, we will find basically the closed loop, a closed form solution for this problem. I can give you some more details offline. I can also share some notes on that if you're interested.
Thanks.
Yeah, may I ask a quick question about like, maybe I missed something obvious. Like, why are the cost functions in these formulations are quadratic? Like, is there a particular reason, or it could be like some other forms of?
Yes, so it's a good question. And for the LQR problem, it has to be quadratic. So for this problem here on the bottom, we want it to be quadratic. And again, this comes from the derivation. On the other hand, in MPC, we can change it. And you can pick the cost function that you prefer. Something that is important to consider is that as you change this cost function, solving this problem is going to be harder and harder and harder. So for instance, if you have here a minus sign, it might be that this cost function is non-convex, and then solving this optimization problem is going to be hard.
Oh, I see. Thank you.
Yeah. Any other questions on these two benchmarks?
Going back a little bit, when you said safety, did you mean like hard constraints or just like any type of constraint that could be like probabilistic or anything else? So in this case, we're going to consider hard constraints. Actually, the case of probabilistic constraint is still under study. There are some technical challenges that we have to face when we have chance constraint. And actually, if you look at the most, I guess, like prestigious journal, every year there are 3 or 4 papers that talk about chance constraint satisfaction. Okay. So now let's see how these two controllers can be used to solve our drone regulation problem. So in this figure on the y-axis, we have the position over the vertical direction, and on the x-axis, we have the velocity. And so here we have an initial condition x of 0, for which we have a positive position and a down-phasing velocity. And so in this example, our constraint set is given by this black box, by this set calligraphic x. And here we see the closed loop trajectories for the LQR and the MPC. And so what we see is that the LQR violates our safety constraints. And this is expected, again, because in the LQR, we do not consider state and input constraints. On the other hand, the MPC realizes that it has to brake and decelerate quite harshly to guarantee that we are actually contained in these safety sets. Okay, so looking at this example, it seems that we have fixed our problem. So we managed to compute a control policy for a constraint system. And as we have just discussed, we can handle linear, nonlinear model, any kind of cost, constraint, delay, and disturbances. The only requirement to apply these strategies is that we need to solve a finite time optimal control problem at each time step. And so this is also the drawback for this strategy, because this might be computationally demanding, right? So let's go back to our problem. it's clear that if we have a longer horizon, then we will have more variables, and as a result, our computational cost will increase. So what we could do in order to fix this problem is simply to plan over a very short horizon. So when we shrink our horizon, the computational cost is going to decrease. But as we're going to see with this cartoon animation, this might cause problems. Okay, so let's say that our initial condition, x at time 0, and again, our state here is two-dimensional. So we have the position at time 0 and the velocity at time 0. Let's say that in this example, we have a positive initial position, but we have a down-phasing velocity. Okay, so we have that the velocity vector is negative and it's pointing downwards. Okay, and so now let's assume that in this problem we want to regulate our system to a goal height, but at the same time we would like to minimize our fuel consumption, right? So we want to minimize our control effort. We don't want to brake too hard and we don't want to accelerate too hard. And so what's going to happen is that our controller might plan an open loop trajectory that barely keeps the trajectory of the system within our state and input constraints. So here in this case, our last predicted point is exactly on our safe region. And so what's going to happen is that when we apply this receding horizon in closed loop, our drone is going to move to the next predicted state. And now we need to compute another open loop plan that keeps the system within our constraint set. However, if we didn't brake hard enough, it might be that our velocity vector is still pointing down with a very high magnitude. And for this reason, it might be that there isn't an open loop sequence of actions that keeps our system within our safety constraints. So what happened is that our controller failed to understand at the previous time step that he had to brake. And this is something that we see, for instance, also in autonomous driving. If we don't detect that the vehicle in front of us is braking and we fail to act because the system has inertia, in the future, we are going to crash. And so here again, I would like to stop for a second to see if there are any questions about this failure mode. Okay. And I also coded up a simple example to convince you that this is something that can happen already with a very simple system. So here on the x-axis, we have the position of our drone. Sorry, on the y-axis, we have the position of our drone, and on the x-axis, we have the velocity. And here I coded up 3 different model predictive controllers with different horizon length. We are applying exactly the same strategy, exactly the same code. We are only changing the horizon length. And so what we see is that when our horizon is long enough, we are actually able, and so this is our starting position, x at time 0. So when our horizon is long enough, our controller actually successfully is able to drive the system to the origin. However, when we have a short horizon, our controller fails to understand that it has to brake. So here again, we have a down-phasing velocity, which is pretty high. And in this example, it's happening exactly what we saw in our animation. So in this figure, again, on the y-axis, we have the position. On the x-axis, we have the velocity. And here I plotted the optimal predicted trajectory at time 0. And so again, we see that the controller planned a trajectory that is barely inside our constraint set.
I have a question about yes. The choice of horizon. Is there any work on, because I can imagine you maybe want to do it like adaptively for some reasons. Is there work on that?
Yes, actually, we are working on something along those lines where you have adaptive horizon. And yeah, there was actually a paper that came up like a couple of months ago on arXiv. So people are actually looking into it. And I think it's a very interesting avenue of research because the horizon, again, affects your computational cost, right? So it would be very interesting to have a strategy where you can change the horizon while guaranteeing safety, because again, you can save computational load.
So what signal do you look for to like respond to when you're trying to adapt the like, do you say like a greedy solution will work well here so I can shrink the horizon, and like in this situation I need Like how do you like tune that, I guess?
Okay, so we are actually going to talk about this and in this class, but the short answer in one sentence is that you always want to make sure that you have a backup plan. But we are going to actually discuss this in this class.
Okay, thank you.
If
Any
you
other
go
questions?
back a slide,
Yes.
So let me just make sure I understand this plot correctly. So I guess my first question is like, why are the red and black lines, like, why are they cut short?
Yes, so what's happening is that the controller, so for instance, let's say this was x0, this was x1, and this was x2. So at time t equal to 2, the system reached this state, x at time 2, and now we are trying to solve our finite time optimal control problem with a batch approach. And what happened is that it doesn't exist a plan that actually keeps the system within this constraint set. So what's happening is that our position is negative and we have a velocity which is pointing down. So now you want to find, and you have acceleration constraints. So you cannot apply infinite deceleration. So you cannot slow down your system infinitesimally fast. So
I see. So the fact that the trajectory isn't continuing is just showing that once you reach that point, there is no controller that is feasible.
Exactly. So, and actually, there is also more than that. There is no controller that can avoid collision. So once you reach this point, you know for sure that with that actuation constraints, you are going to crash.
Thanks.
Yeah. So I guess like another example is the autonomous cruise control. So it might be that if your vehicle is traveling at a velocity which is too high and the vehicle in front stopped, even if you have not reached collision, you know that you cannot decelerate fast enough to avoid that collision. So in this figure, at these 2 points, we have reached this situation. And here, what's important to underline is that the system reached this point from which we cannot avoid collision, but all trajectories started from the same initial point. So our controller took the wrong decision, applied the wrong control action at time t equal to 0.
Could this be avoided if you make QF larger, like you make the cost of like not going to the target bigger?
Yes, yes. And so actually we are going to work a condition similar to what you said. We are going to use terminal constraints to avoid this problem.
But I guess I thought there was a terminal constraint already.
Yes, but like the terminal constraint right now is our terminal set. So what you want to do is that you want to be more conservative and you want to force your plan to go close to the origin. So if you look, so our terminal constraint in this case was calligraphic X, so was our safe region.
I see. So it wasn't actually the origin?
Yes, exactly.
Oh, thanks. Okay, that helps.
Any other questions about this feasibility issue?
Sorry, just quickly, like it seems like what you're given the constraints in like position space, but what you really want to know is like what's the safe region of the phase space, which is like not obvious, but it seems like you could use like that somewhere. You could use learning as to like sample points of phase space and check whether they're safe, and then like I don't know.
Yes. So you're going in a great direction. This is actually what we will be doing like next class. We will use learning to understand where we can plan and where it's safe to plan.
Nice.
And the other thing that we will use learning for is to reduce the optimality gap. So when we plan using this receding horizon strategy, in general, we lose optimality. So in this figure, we see the closed loop trajectory associated with the MPC controller in blue and the optimal trajectory. So for this simple problem, I was actually able to compute the infinite time, the solution to the infinite time constraint control problem, and we see that there is an optimality gap. So our controller is suboptimal. Okay, so in this first part of the class, we have seen that the MPC might take short-sighted control action that would lead to feasibility, stability, and optimalities issues. So the first question that I would like to answer is like, why do we care about these issues if we want to design, for instance, model-based reinforcement learning strategies? And so I wanted to briefly give you an overview of a state-of-the-art algorithm in model-based reinforcement learning. So this is a paper that came out from Berkeley in 2018 and proposed the PATS algorithm, which stands for Probabilistic Ensemble with Trajectory Sampling. This paper actually was really important, and if you are interested in model-based RL, I highly recommend reading this paper. And really what this paper showed is that model-based reinforcement learning strategy can achieve the same asymptotic performance of model-free while requiring significantly fewer samples. And so actually this paper was a big deal when it came out and steered a lot of people's research towards model-based reinforcement learning. So I wanted to give you only a very high-level description of what this paper is actually doing. So the key idea of this paper was to use historical data to train an ensemble of deep neural networks, which can then be used to forecast the trajectory of the system. So here the authors assume that the model is unknown. They use historical data to train an ensemble of deep neural networks, and then they use forward propagation to solve a planning problem. And then they computed a policy solving this planning problem at each time step. So basically they use a model predictive control strategy. And so the key idea and the reason why I wanted to introduce this paper is that also in this very complicated setup, we are going to have exactly the same feasibility issues that we saw in our toy double integrator example. So I want to stop for a second to see if there are any questions about this strategy. Okay. And so what we did actually is that we built upon this strategy PATS, and this is really some amazing work done by Ashwin and Brijan, which are two PhD students with Professor Ken Goldberg at Berkeley. And the idea of Ashwin and Brijan was to merge strategies from control and MBRL to solve this feasibility issue. And what they did is also that they implemented their algorithm on a real robot. And on top of that, they did a very nice study where they benchmarked their strategy against different state-of-the-art methodology, including PATS, safe actor critic, and some other strategies. And in their examples, they were solving a problem which is very similar to the problem that we are looking at. So they had a starting state and a goal state. So here. And in this set of examples, they wanted to drive the system from a starting state to a goal state while avoiding some obstacles. And again, their idea was to merge strategies from the model-based RL and the control community to guarantee safety. And so hopefully with this example, I've convinced you why it's interesting and it's important to look at this recursive feasibility issue in receding horizon planning.
A quick comment.
Yes.
Yeah, so for those of you who don't know, Ashwin Balakrishna was a Caltech undergrad and
Yes.
actually took CS 159, I think 4 years ago, starting him down this path. So for those who are undergrads taking this class, you know, these are the right times to start thinking about how to transition to, you know, interesting research in your career if that's something you're interested in.
Mm-hmm. Yeah, and also, yeah, indeed, he was an undergrad at Caltech, and indeed also some really amazing work, both on model-free and model-based. So he really had like the full perspective on the problem.
any other questions about why we're going to spend the rest of the class looking into this feasibility issue in receding horizon planning?
I have a question, which is, if your like constraint, your feasibility constraint, would like if you moved your cost to it and then you just like pumped the cost up constraint until like the optimality solution, like feasibility would look exactly like optimality. And so, does that make sense? Does that question make sense?
Could you repeat? Actually, I don't think I'm following. I think feasibility and optimality are two different issues. But
right. But let's say you have some condition. Let's say you have a cost function that's a function of only state, and
yes.
Your constraint is like, I want my cost function to remain below a certain value.
Mm-hmm.
And then you just moved that value like to like C star, which is the optimal thing. So then feasibility and optimality in that way.
Okay.
Right, because if you're feasible, then you're also optimal. I was just wondering what, like, when you're designing these things, how do you think about, I don't know, would like this like sparse cost thing, it starts to, you know, look a little bit like, I don't know, like intense feasibility rather than optimality.
Yes. Okay. So basically, let me reformulate your question. So what you're saying is that when you have constraints, you can move these constraints to the cost, assigning a very high penalty. And so usually this is done, for instance, assigning infinite cost to some states that you don't want to visit. So what happens in that case is that your optimization problem becomes really challenging. And the other point that you said is that optimality and feasibility are the same. Yeah, it's basically when you put your constraint into the cost, but in general, we would like to have like hard guarantees. So we would like to consider really hard constraints in our problem. So every time that you relax the constraint and you put them into the cost, then constraint violation might occur. And actually what would happen is that if you take your constraints and put them in the cost, in some cases, there might be a feasible solution, but your optimizer will return to you a solution that violates the state constraints simply because from a cost point of view is more optimal.
Yeah, that makes sense. Thanks.
Mm-hmm.
I guess the reason why I was asking, sorry, is because this task to me looks like something that the robotics community would solve with like a sampling-based planner, like RRT or something like that.
Yeah.
Which is like, you know, it grows a tree, and there are like formulations of RRT that use like that have optimality guarantees and stuff like that. So it's kind of like RRT is a feasibility algorithm.
Yeah.
Plain RRT is feasibility.
So I mean, first of all, like these optimized is like given motion primitives, right? So you're really sampling the state space. And so what I do think that at the end, when we will implement these algorithms in the real world, we will have an RRT that samples some trajectory, and then we will use this optimization-based strategy to compute a smooth trajectory. So for instance, if you're trying to solve a parking problem with an RRT, the trajectory that you will plan is going to have a lot of kinks, and this is not something that you really want to put on hardware.
Sounds good, thanks.
Mm-hmm. Any other questions? Okay. So now let's see how we can actually fix this feasibility issue. And we're going to fix this feasibility issue considering how the planet trajectory changes at different time steps. So as we have seen in our previous animation, as time passes and we keep planning, our open loop plan changes. And in order to guarantee safety, what we need to do is that we need to distinguish between the optimal plan at time t and the optimal plan at time t+1. So in order to do so, we are going to introduce this notation. So u at time k given t is the input that we will apply at time k if we follow the plan computed at time t. And so the reason why we are using this notation with this conditioning is really simply to distinguish between the optimal plan at time t
and the optimal plan at time t+1. Any questions about this notation? Okay. And so in order to fix our feasibility issue, what we are going to do is that we will design the terminal cost and the terminal constraint of our receding horizon strategy in order to approximate the tail of the cost and the constraints beyond our prediction horizon. So let's consider again our drone regulation problem, where we had issues as our controller was planning an open loop trajectory that barely kept the system within our state and input constraints. And so in order to fix this problem, what we really want is that our terminal predicted state should be close to our goal position. So in order to fix this problem, we are going to consider a terminal constraint set. And the key property that we want is a guarantee about the feasibility of our plan. So we want to make sure that once we start our controller, at each time t, our optimization algorithm will return an optimal control action. And so this problem in the predictive control community is called recursive feasibility. And recursive feasibility is the property that states if at time t the MPC problem is feasible, then the MPC problem, our optimization problem solved with a batch approach, is going to be feasible at the next time step. So this is really the key property that we would like to guarantee. And furthermore, the second property that we would like to guarantee is that if our goal is to reach a point, we are going to reach the point, or we are going to reach a neighborhood of that point in finite time. And this property is called stability, which informally tells us that as time goes to infinity, the norm of our state goes to 0. So we reach our terminal point. So, and again, here I want to stop to see if there are any questions about the two properties that we would like to guarantee when we design receding horizon controllers. Okay. So now let's see how we can guarantee a controller that satisfies our state and input constraints using a terminal constraint set. So we are going to assume that our terminal constraint set is the origin. And notice that the origin is an unforced equilibrium point for the system. So this means that if we have reached the origin and we don't apply a control action, we stay there, right? So if we apply 0 acceleration and our velocity is 0, we're going to stay in a particular place at the same, sorry, at our origin, which represents the height where we want to hover our system. And so what we're going to assume, that at time t equal to 0, our model predictive controller is feasible. So we can solve a batch approach. So with a batch approach, we can plan a trajectory that drives our system to the origin. And then in a receding horizon fashion, we're going to apply first element of the optimizer vector. So our drone at time t+1 will move to our predicted state at time t+1. So here we don't have model mismatch. So our system evolves exactly where we want it to. And now what we notice is that what we notice is that at time t+1, we actually do know that there is a feasible trajectory to our finite time optimal control problem. Indeed, we can simply reuse the trajectory that we planned at the previous time step to steer our system to the origin. And once we are at the origin, because it's an equilibrium point, we can stay there. So with this simple fix, what we realize is that we have a feasible trajectory that can be computed simply appending the equilibrium point and applying an input that is equal to 0. And so this plan really guarantees that the next time step t+1, our model predictive controller is feasible. And now I would like to stop for a second to see if there are any questions about this, this property. Okay, so now let's see how we can use a similar approach to guarantee stability, how we can guarantee that our system converges to the origin. We're going to consider exactly the same setup where our goal is to regulate the drone to the origin. And here recall that in our drone hovering problem, our instantaneous cost h was a quadratic term. So we have that this cost is going to be 0 only when we are at the origin. And we are going to assume that our terminal cost function is also a quadratic term. And so the proof, again, so first of all, what we are trying to show here. So what we are trying to show is that the open loop cost of this MPC strategy goes to 0. So why we want to show that the open loop cost of our controller goes to 0? We want to show that the cost goes to 0 as our cost is given by the summation of the stage cost h and on the terminal cost. So if we manage to show that the open loop cost of the MPC goes to 0, then we have shown that our system is converging to the terminal goal point. And so again, the proof is as simple as before. We assume that at time t0, we have a first feasible trajectory. So sorry, at time t0, we can solve the finite time optimal control problem. And therefore, there is a plan that is able to drive the system to the origin. Again, in a receding horizon fashion, we are going to apply the first element of our optimizer vector. So the system is going to move to the first predicted point. And now what we notice is that, again, we have a feasible trajectory to our optimal control problem that can be used reusing the optimal plan computed at the previous time step. And so now what we notice is that, so let's consider this trajectory in red, which is again a feasible trajectory at time t+1. What we notice is that the optimal cost associated with, sorry, that the cost associated with this feasible trajectory is equal to the cost associated with the trajectory that we computed at the previous time step. So this is J minus the stage cost evaluated at our initial point. So this was the stage cost at xt given t, comma ut given t. And so this is simply, and so this relationship is true again, because once we reach the origin, our cost is equal to 0. So the cost associated with the plan in red here is equal to the cost associated with the plan in blue minus the stage cost. And so now, any questions about this? Okay. So now what we notice is that this is the cost associated with a feasible trajectory to our finite time optimal control problem. And so fast forward, we see that by virtue of being the cost associated with a feasible trajectory, the optimal cost of our controller is going to be lower or equal than that. And now what we notice is that by definition, this quantity is strictly greater than 0 because we started with an initial condition that is different from the origin. And so here we are subtracting strictly positive term. So this means that our open loop cost is strictly decreasing, which in turn implies that the limit goes to 0 and that our system is closed loop stable. So any questions about this second derivation? Okay. And so what I also wanted to show with a simple simulation is what happened to the open loop cost when we use the terminal constraint set as the origin versus when we use our entire feasible space as a terminal constraint set. So here on the y-axis we have the open loop cost, and on the x-axis we have the time. So what we see here is that when we design the model predictive controller correctly, our open loop cost decreases and actually follows like the decrease is exponential. On the other hand, when we don't use the terminal when we don't use the origin as a terminal constraint, our cost first goes up and then goes down. And this is because, again, we lose all the theoretical guarantees.
And so the key message from this first part of the lecture is that when we don't design correctly the MPC terminal components, then the closed loop system might violate state and input constraints, and convergence to the terminal state is not guaranteed. And so what we saw today is that a solution to fix this problem is to use zero, or an equilibrium point as a terminal constraint, and to set our terminal cost equal to zero. And so with this strategy, we managed to guarantee feasibility at all time instances, and we guarantee that our optimal cost is decreasing. However, there is, of course, a main drawback, and the main drawback is that the region of the state space from which we can control the system is going to shrink. So the region of attraction of our controller is going to shrink. So what I mean by that, let's take a look at this figure where, again, on the y-axis, we have the position, and on the x-axis, we have the velocity. So in this figure, this dashed black line represents our constraint set of our drone hovering problem. And here with this black polytope, I represented all the states from which is possible to steer our system to the origin. So this means that if we pick an initial condition, x0, which is outside our black polytope, then our model predictive controller will be unfeasible. And of course, this issue might be fixed simply having a longer prediction horizon. And so here what we see is that as our prediction horizon is longer, we can stabilize a bigger set of states to the origin. And this region is going to grow, again, as we design our controller with longer and longer prediction horizon. However, again, we fixed one problem, but the other problem came up. So now we need to plan with a long prediction horizon, and we will have problems related with the computational tractability of our problem. So here again, I want to stop for a second to see if there are any questions about the region of attraction of the controller.
Hey, Hugo, can I ask a question? But it's about the convergence stuff. So I'm wondering, MPC literature, is it possible to show its kind of exponentially convergence, not just asymptotically, without explicitly giving the formula of the policy?
So the closed loop system is nonlinear, right? Because the MPC policy is nonlinear. So
right,
yeah, asymptotic stability doesn't involve exponential stability. So yeah, I have to check, but like I don't see a straightforward way to prove that.
I see, because it's possible that even this asymptotic converge to zero, but may takes very, very long time, such that this problem is kind of implicitly infeasible in some sense. I'm not sure whether it's possible in practice.
So I mean, first of all, it's not unfeasible that it will reach. So if it's asymptotically stable, you will get there in an infinite amount of time. However, what you know is that for all practical purposes, if you want to reach a neighborhood of your goal state, which is epsilon close, you will get there in finite time, right? So this is, I guess, the property that we care about in practical applications.
Okay, thanks.
May I ask a question? So could you go back like maybe one or two? Like I see why like the JT star is like secretly decreasing, but could it like converge to like some, I don't know, positive value? Like why does it have to converge to zero? Is it because we set the XF to be zero?
Yes.
Like calligraphic F.
Yes. So the idea is that we want. So in this example, we want to drive the system to the origin. Yeah. But in general, if you want to drive the system to an equilibrium point, you want to make sure that your instantaneous cost and your terminal cost are zero when you reach the goal point. And so this implies that your optimal cost is going to be zero whenever you reach the terminal point, and it's going to be strictly positive when you have not reached the equilibrium point where you want to go. So this quantity is either positive or equal to zero if you've reached the goal point. And so what we showed is that, again, back one slide. So the stage cost again is strictly greater than 0 if we are not at our equilibrium point.
Oh, I see.
So this quantity is going to be strictly greater than 0. And so we can relax this inequality to a strict inequality.
I see. And then you can keep like lowering like J star, minimizing J star if you like keep driving it to the origin until you reach there, in which case you will get a 0 J star.
Exactly. And so the key idea is that, and this is really in receding horizon control, all the proofs in all the literature are done by induction. And this is exactly what we did in this proof. So we assumed, so we started with our assumption, which was, let's assume that at time t, our controller is feasible. Then we show that at the next time step, our controller is again feasible. So now you see that you can iterate this induction argument to show the properties over an infinite horizon.
I see.
This also requires like closeness and compactness of the set you're working in, right? Otherwise, I can go off into infinity and like the rate at which h is always going to be the thing you're subtracting is non-negative, is positive, but it's going to 0 faster than j is going to 0. Is
yeah,
that
so usually, so the assumption that we really required is that the origin, both of the constraint is inside the constraint set at the input set. But so I guess like here you're asking if this so because you're really subtracting these quantities, so you're asking if the summation of these quantities can converge to a constant value.
We're asking the question, yeah. Mm-hmm.
Yeah, and I assume that like, yeah, no, still you're going to decrease, right? Still your cost is going to decrease.
I have a question regarding that actually.
Yeah, I guess like, so wait one second, let me actually come back. So if this thing goes to 0, then it means that like so the only way for this thing to converge is that h goes to 0, right? And so when h goes to 0, you go to the terminal point.
I see. Okay, thank you.
So my question was about the feasibility analysis. So in your feasibility proof, it looks like you're expecting the actual system dynamics to behave the exact way that you had planned in your MPC trajectory.
Yes.
So is that in general how feasibility analysis are done, or because I think one reason why people prefer MPC is because you have this almost like robustness. For every new time step, you actually measure your state, and then you get to start from a new starting point. So that x star t plus 1 may not be the true x t plus 1.
Yes. So this is a great question. I think your volume was a bit low, so let me repeat the questions for everyone. So your colleague is asking if the fact that here we are assuming that the system dynamics are exact might cause feasibility issues. And the reason is absolutely yes. And this has been something that has been studied in MPC. And the reason to get around this issue, I'm gonna sketch on this figure. The idea is that when we know the model uncertainty, so let me actually go back to the initial figure. So let's say that we are given the model uncertainty. So we know that our true system will not evolve exactly as our planning model. What we are going to do is that instead of planning a trajectory, we are going to be planning sets. So the idea is that you will plan, instead of planning a trajectory, you will plan a sequence of sets which will contain your model for all possible time instances. And then what you will make sure when using this strategy, the key idea is to plan these sets so that those sets are disjoint with the constraint sets. And then at the next time step, even if the system doesn't go exactly in the center of the set, but it gets somewhere close, you can still guarantee recursive feasibility when you have uncertainty. So when you have a model mismatch between the true system
and actually the nominal dynamics. So usually we use this term. The nominal dynamics are the dynamics using the MPC controller. And there is like a big body of literature that can be used to do so. It relies either on sampling-based strategies or actually on robust optimization. And I'd be happy to forward you like some papers if you are interested in this. But it's still actually a topic of ongoing research, because it's really hard to make these plans while being computationally feasible. So computing these sets, these are called reachable sets. So computing these sets is computationally very intense.
I see. Thank you.
I have a question on the slide with the multiple sets for different time horizons and the region of attraction.
Yes, so let me go to that slide. I believe it's this one, right?
No, or maybe I'm not saying it, but.
Okay, yeah, it seems that like there's something going wrong on my end. Okay, let me try sharing my screen again, because I actually see it on my iPad. Sorry about that.
No problem.
Okay, so let me 1 second try to disconnect my iPad. Not sure what's happening. Okay. So one more trial. So maybe I can switch to a slide set and just sharing my screen. I guess that would work as well. So let me open the slide set, the Acrobat. Okay. So there should be probably a window. Okay, can you see my screen?
Yeah, we can see it.
Okay,
or I can see it.
Okay, let me get to that slide. Yeah, sorry about that. Not sure what's happening with my iPad. Okay.
Right.
I wait 1 second. Yeah, sorry. Okay, here we go. Finally, we made it.
Okay, so I don't think I follow very well, but there's a region of attraction. What is the definition of that? Is it where the MPC is feasible?
Yes. So what we showed is that if the MPC is feasible at time t equal to 0, then the MPC will be feasible at all time instances, and our cost is going to decrease. Our open loop cost is going to decrease, which in turn implies that if our model predictive controller is feasible at time 0, then you will converge to the origin. And so the definition of the region of attraction is the set of points from which our controller will drive the system to the origin.
Okay, so thanks. That makes sense. I guess where I'm and then the key point is that the feasibility set is a function of your horizon. So where I'm stuck is or what I'm thinking about, it kind of relates to the previous question about the path planning algorithms and like where do you use MPC versus path planning? And I imagine if you have like path planning aren't optimization solvers, they're tree-based solvers, but like if you try to do path planning with an optimization thing, like what this is saying is that as soon as you have enough time steps to feasibly reach the goal through whatever maze you could possibly go through, optimization will solve it. And I feel like that's putting a lot of stress on the solver. And
yes, exactly,
I just kind of wanted to hear the summary of that, I guess.
Yeah, exactly. So what we're seeing here is that we fix one problem, but we run into another issue, which is exactly what you're pointing out. That in order to have all these nice guarantees, we really need an horizon which is long enough.
which might be, not a good idea in several applications. So for instance, if you want to plan your trajectory from Pasadena to LAX, you don't want to plan from here to the airport, right? And what we are going to see actually that this problem can be mitigated by designing terminal sets, which are a set of states from which you can complete the task. And we will see this in the next lecture. We will see how we can use learning actually to design these sets. Does this answer your question?
It does, because basically these terminal sets would be like intermediate solutions kind of that would help you plan as you go. So
exactly.
Yeah, sorry. So one question that I had about this, actually, no, I'm fine. Thank you. That's great. Thanks.
Okay, yeah. And if you want to chat on how to integrate RT-based solution with MPC, that would be also a very interesting project. And we have actually done some work in that direction. So if you want to chat about it offline, I'd be happy to give you a more detailed perspective on that.
Thanks.
Any other questions about these stability and recursive feasibility issues in receding horizon planning? Okay, then I'll move to the last topic of today, which is going to be about nonlinear systems. And so we will focus on an autonomous racing example where we want to control a car, and actually we will have an objective which looks like our regulation problem. So our goal is going to be to drive our autonomous car to the origin. And so what we noticed is that actually our derivations did not rely on linearity of the system. And so actually, do you see my screen right now? And can you see also the pointer? Okay, yes. Great. So our derivations did not rely on linearity, right? So we can repeat exactly the same proof that we did for the linear case. So we can assume at time t equal to 0, that there exists a feasible trajectory that can drive our system to the origin, and then we can apply the first control action. And again, once again, we have a feasible trajectory that drives the system to the origin. And the only reason why I wanted to show this strategy also for nonlinear system is because in nonlinear system, this feasible trajectory really carries very important information. So this feasible trajectory can be used when we have nonlinear systems to linearize our system dynamics. And this is going to help us when we want to solve model predictive or receding horizon planning in general for nonlinear systems. So let's say that at time t+1, our system has moved to the first predicted point. Now we can use the planned trajectory at the previous time step t, and here we see why we're using this idly notation, because again, we want to keep track on when we planned a specific trajectory. So now we can use this trajectory to linearize our system dynamics. And what you will see actually also in your homework is that when you use this strategy, you can actually beat commercial solvers for general purpose solvers, which are used for nonlinear planning. And so the key idea is that we can use this strategy as the planned trajectory at the new time step is going to be somewhere close to the old predicted trajectory. And for this reason, our linearization is going to be accurate. And so actually with this, I wanted to wrap up this lecture. So these were the key concepts that I wanted to discuss today. I wanted to give you a brief overview on what's next. So in the next lecture, we will see how we can iteratively construct the terminal components of our model predictive controller to enlarge the region of attraction while guaranteeing safety. And so as I see that there is still some time left, I will be online if you guys have any questions about this lecture or the previous lectures.
So just to clarify,
Mhm.
today we did not talk about actually defining the final terminal constraint set, right? That's what we're going to cover in next lecture.
Yes, yes. Today
Okay.
we just saw that if we pick a point which is an equilibrium point, then you can guarantee safety and stability.
So yeah, so the whole assumption was that we were able to, that we are already within the region of attraction.
Yes, and that region of attraction, yeah, you can compute it. So this region of attraction is the set of points from which you can drive your system to the origin.
I see. I guess, so kind of going back to, I forget whoever asked the adaptive horizon problem, but like, so suppose you realize, oh, I'm currently not in the region of attraction, is like one strategy then, okay, let's try more compute by extending the horizon.
Yes, that's definitely something that you could be doing, yes.
Makes sense, thanks.
Yeah. However, what you want to do in general is to compute these sets before deploying your controller on experimental hardware, right? So you want to have some kind of safety guarantees that says like, oh, if my controller is in this part of the state space, I'm actually safe. And we will not cover how to compute these sets, but I'm going to give you some lecture notes that you can go through in case you are interested. So these sets are computed using projection operations, and actually computing these sets is pretty hard already for linear system with state and input constraints.
Thanks.
Hey, I have a very pretty high level question. So, because another way to use MPC, if I understand correctly, especially in robotics and the chemical process control, for example, is we abandon the U output. We only take the desired, the planned trajectory. And there's another low-level controller trying to track this planned trajectory. So in other words, MPC is only used to generate the future in horizon, like desired trajectory. So could you comment on like the difference? It's it's very hard to have any guarantee for the case I just described, because
yeah, actually it's not, and we have some very like recent work here at Caltech on doing so. But the key idea is that you would like to have agreements between these two different layers. So what you're saying is that we have a planner that is based on MPC and gives a reference trajectory that we want to track. So then what you could do is that you can use basically standard approaches from the MPC literature to guarantee safety. Because what's really happening is that your tracking controller, from an MPC perspective, is simply a disturbance. Right. So what's going to happen is that the next time step, you're not where you wanted to be, you are in some neighborhood. And so this really means that you can robustify against that.
I see, thanks. And also a follow-up question is, since you mentioned the computational cost would be an issue, and in the online learning literature, is there something like we move horizon like every k time step, which means we execute UK plus 1 and until UK plus 2, which means we only need to replan every k time steps. So I'm wondering, do you know some like analysis like this in this case?
No, actually, I've seen something which is the other way around. So what you wanted to do is that you downsample the MPC. So you solve the MPC problem every other time step. I've seen something which is different, where you have a very high frequency for the first predicted state, and then a very low frequency for the rest of your planet trajectory. And so this basically allows you to have few optimization variables to plan far ahead in the future. But I think that the strategy you proposed, it's possible to use standard tools to show safety, recursive feasibility, and stability.
Thanks.
For the nonlinear systems, I was just wondering generally what kinds of constraints you have to have on the systems to make the approximations reasonable.
Yes, so this is actually a great question. And so what you can think of doing is that now here you're linearizing your state around the previous optimal solution that you compute at the previous time step. So something that you could do is to have some cost that penalizes the difference between the new planet trajectory and the old point where you have linearized. So in general, you want to have some constraint or cost that forces your controller to plan a trajectory close to the linearization points. And the reason why you might want to do that is because you are linearizing the system dynamics around a particular point, and so your model is accurate only in a neighborhood of that point. And so this is actually something which is important also when your model is learned from historical data. So you might want to use confidence intervals to define where you can plan.
I think another aspect of the question being asked, Ugo, is what assumptions do you need to make on a nonlinear system? Like, for example, it's second order Lipschitz constant.
Yes. So it has to be smooth. The system has to be smooth and differentiable.
Yeah, and then the Lipschitz constant on the derivative determines the size of the neighborhood.
Yes. So if you want to like start having formal guarantees about like how far you can plan from the linearization point, you have exactly to quantify that uncertainty, and Lipschitz is a strategy of doing that.
Okay, thanks.
Also on the nonlinear system, when we're replanning with these linearizations, are we assuming there's a disturbance that's knocked us off of the like plan trajectory, so it's suboptimal, or are we assuming that the original plan trajectory is for some reason known to be suboptimal when we're like maybe doing online learning? I guess I'm trying to understand what scenario would we have moved forward on a trajectory need to correct using this linearization.
Okay, so this strategy that I'm presenting here is actually like not rigorous. To have like rigorous guarantees, you need to consider like the uncertainties. So you would need to do two things. The first one is what Isam mentioned, that you need to understand which is the region around the linearization point for which your model is valid. And the second one is that you will need to plan robustly. So you will need not to plan only a nominal trajectory, but a set, so a sequence of sets that will contain your system dynamics. So if you want to consider disturbances, you need to plan robustly.
I guess maybe a better way of phrasing so we have the old plan trajectory, and I guess the question is, if we're following it, what was wrong with it? And like, what did we not know before that we now know that we're replanning?
Oh, okay. So
like, why are we, what's triggering the replan?
Yeah, no, definitely. Like you need to replan because you have, in general, uncertainty in the system.
Okay.
Yeah.
So it's a system of uncertainty.
Yeah, but again, as we saw, if you don't have this terminal constraint, even if everything was deterministic, you could have failure. And the reason is because you're not planning far ahead.
Yeah, because in general, without it, we might have to replan because it's no longer feasible further when we see further on the horizon. But here we have that terminal constraint, right?
Yes. So here the only reason for replanning is that when you want to put this on a real system, you will have disturbances.
Okay, makes sense.
Maybe just to go back to Ugo's analogy about driving from here to LAX. If you drive from Caltech to LAX, are you going to preemptively plan every steering angle your arm makes on the steering wheel and every amount of pressure you put on the gas pedal and brakes from here to LAX pre-planned? So there's the issues that Ugo mentioned in terms of long planning horizon, feasibility, and uncertainty in the model, because you don't exactly understand exactly how the car works, right? It's a little bit of a feedback mechanism there. All those things come into play.
Yeah, it just looked like from the diagram that this was the situation where we had planned all the way to the feasible set where we were at the equilibrium. And I guess the follow-up question I wanted to ask was like, could this be used as a framework for online? Like, I don't know if learning is the right word, but we're like, we need to get moving. So we come up with a feasible but potentially suboptimal trajectory. and then each time as we move, we replan. Maybe we have computation time to like replan. I think you said like 10 hertz in a previous lecture. So we're just like, is that something that maybe is done of using like a feasible but maybe not great trajectory, and as we adjust, just replan to a better trajectory as we move along?
Yes, this is done all the time, like in both in practice and in theory. And in general, when we have nonlinear systems, we really have to give up on optimality. So something that we actually didn't discuss today is that we are really, so for all these proofs, we are really assuming that our batch approach spits out the optimal solution. So another question is like, what happened when like you have a nonlinear model and then your optimizer, like your routine, your solver, gives you something that is suboptimal, and how do you improve on that? And so in that case, replanning helps. And actually, you're gonna see this in your homeworks, where you will see that like keep replanning, you will adjust for optimality.
Thank you. Interesting things to think about.
May I ask a clarifying question? Like, so the major difference between this lecture and the previous lecture is that the action state and action space are spaces are continuous rather than discrete, right?
So
like
this
any
is
other difference?
Yeah, from lecture one, but yes. So there are two main differences. One is like the one that you mentioned, and the second one is that here we have state and input constraints. So in lecture one, we assume that the cost at each state had to be finite. And that assumption basically implies that we cannot handle constraints. Because ideally what you would do if you want not to visit a state is that you would assign infinite cost. So in the first lecture, we saw how to solve problems where there are discrete, the state space is discrete, and we didn't have state and input constraints.
Okay. But I think for the second lecture, there, like, we discussed like the constraint, like linear, whatever. Like in that problem, we do have those constraints, right?
Yes. So basically in the second lecture, we simply saw how to solve an optimal control problem at each time step. So how you can reformulate your problem and solve it using a batch approach.
I see.
So basically we saw how to compute an open loop sequence of actions and states. And in this class, we are seeing how we can iteratively use that strategy to compute a control policy.
All right. Yeah, thank you. That helps a lot.
Thanks. Any other questions?